Ladies and gentlemen, I would like to present the output from our scientific group and research group in Slovak University of Technology in cooperation with the University of Pilsen, West Bohemia. And the title is Analysis of the Specificity of Static Properties in Additively Manufactured Metallic Materials. Content of my presentation is a bit large. I try to go briefly introduction, specific of this material. I try to a little bit summarize and generalize it. Then introduction of these three materials which we investigate, SM curve and Citra. Then tension torsion cyclic test, the multi-axiality. Then selected for comparison with selected multi-axial criteria and some discussing about the problems. Then simulation of defect orientation in additive manufactured cross-section. Then conclusions. In additive manufacturing of metals, this is relatively about 50 years when appeared this technology, selected laser melting, which became to the reality, this additive manufacturing metals. This direct use of these components from additive manufacturing metals is still limited in real operation till this time. Gold is the lower fatigue properties that operation with cyclic or variable loading. This is the problem with these additive manufactured metals parts. Then exist last 30 years thousand criterion which was formulated in the area of multi-axial fatigue. And till this time, non-exist universality applicable criterion for conventional materials, for conventionals. And now we try to say and discussing about the additionally manufactured materials which become with new specifics. Is the topic of my presentation. Before the fatigue materials, very briefly I mentioned the strength properties. This is true documentation about the influence of additive manufacturing to the strength. On the left is the aluminum alloy ALS-I10, as I mentioned Kučerková before. Here is documented the increase the strength of additive manufacturing in the comparison of conventional casting. Second is the stainless steel, which is documented a little bit decrease the strength from additive manufacturing technology in the comparison of conventional casting. That this additive manufacturing can influence on the positive side, also a little bit on the negative side. More often is this case because cooling rate and quenching process, which is the 3D printed process, is possible to say increase the strength in this first step. Another problem is the anisotropy. This is very bad for us as engineers. Here's the documented the influence anisotropy for this aluminum alloy. This is the three different orientation of field process. And the effect of this field process of this orientation to the ultimate stress, yield stress, and ductility is here. Is visible, but is not so huge. The exists anisotropy also in static or static strength, but it's not so catastrophic. It's acceptable, it's possible to say. But I try to summarize the new problems in additive manufacturing technology in the metals. And then I individually will be discussing about these four specifics. This first is anisotropy. I mentioned in the strength. I will discuss in the cyclic properties this anisotropy. Then internal defects, yes, was caused by the thermodynamics of the AM process. Then surface layer condition also is caused by thermodynamics of the AM process. And then non-standard ratio between the SM curve, which was mentioned the first day, here, not Professor Kurek. And then some conclusion from this that I individually mentioned about this four specifics. Here's the well-documented this thermodynamic process in this paper, which was also simulate this thermodynamic process in the same areas. Is documented that on the tip of the laser are very specific conditions which create the vapor, which create the tubular behaviors and many other. And this problem, this thermodynamics of this tip of the laser beam, create these problems with defect, create this problem with firing of the surface and other. Here is the documented this surface problem, that surface roughness. This is one of the specific of the AM technology. On the left is this aluminum alloy. In the cross section are visible these defects. On the right bottom, this is the stainless steel 316L, which is visible this biting problem on the outside surface. Problem with this roughness, both this clay can increase roughness. Problem is when you apply the turning process, for example, for this additive manufactured parts, as here, this defect become to the surface. That problems with high roughness is still. Some solution exists, some solution is the cold spraying, some solution is also this high frequency mechanical impact, some polishing and other. But this is the increase the cost of the producing of this metal part by this new additive technology. This is the problem of the surface roughness. Defects. This is the key problem of this technology, additive technology. It's possible to say that, or it's possible to separate this defect to two different groups from the geometrical shape. First group is relatively kindly. It's possible to say this, which is similar to the circle. The distribution of stresses and strains around this shape is relatively friendly for engineers. It's possible to say. And second group is very dangerous. This is this type, and this is very sharp defect. This first is relatively kindly. Here's the documented. This is only one of the many cases when crack growth is around, not directly through this nice shape defects of around. The distribution of stresses is relatively appropriate. It's not possible to say this is positive, but it's not so dangerous as that is one. This is the key problem of additive manufactured materials. Now, anisotropy in cyclic properties is also a problem. Here is documented on the aluminum alloy, and here is documented on the merging steel. It's not the same. Here is the more visible. This is the horizontal oriented build process. Here is the vertical oriented build process. Difference is visible. In the merging steel, this difference is very, very low, but also exists. It depends on the type of material, of activity of this material, many other parameters, but anisotropy is a problem of additive manufactured metals. Now I try to deeply investigate these three materials which we measured in our laboratories. Both or all this specimen was produced in Pilsen, which is one of the leading company or leading university in the 3D printing of metals. This is the aluminum alloy, merging steel, and stainless steel is the chemical composition. Now the fatigue properties of these materials, some because these results are very, very large. Here's the first on the left side is documented the anisotropy in comparison with conventional casting. This first line is conventional casting, SN curve in pure tension pressure. If you compare in the, for example, conventional fatigue limit, is documented 71 vertical build process, 83 in horizontal build process, 110 in conventional casting. All these materials are compared only between the technologies, not heat treatment, not other surface polishing, not on as built without the heat treatment. This is the difference. In the what is it? This is the merging steel. Also, this is the conventional, and this is the horizontal and vertical. This is the difference. Difference in stresses seems to be not so high, one of 50%, but difference in lifetime here is documented is 1 order and more. This is big difference due to this anisotropy. Here's the ratio between the SN curve in normal stress, that tension pressure, and alternate torsional here, the shear stresses. First is for stainless steel. This ratio is important. This curve is possible to say are parallel, similar to the parallel. In conventional, this is conventional technology. Additive manufacturing is not so pure parallel, but similar to the parallel. For this aluminum alloy, that's rather different. Here is the parallel in conventional technology. In additively, rather no parallel. With the very big problem for the computational calculation of or prediction of fatigue lifetime if this parallelism is not real. Then I try to generalize it. This is this three materials, what I say. Here's the aluminum alloy. This orange probably is the conventional normal stress shear stress parallel. In additive manufacturing, this blue non-parallel. In stainless steel, in AM materials, parallel. So this is not only additive manufacturing. And here this merging steel, also only additive manufacturing, non-parallel. Here is documented that most often situation is non-parallelism between this descent curve in normal stress and shear stresses. This is true. It is relatively not so often. It's opposite situation as in conventional materials. In conventional metals, this parallelism is 99%. Here, it's majority non-parallelism. It depends on the many factors. Probably here is possible to mention that this material is more ductile. Parallelism. These are low ductile, no parallelism. It's only one of the parts. Then we investigate multi-axial fatigue, that combination normal and shear stress into form. Here is the in-phase, this is out-phase, or okay, it's in-phase and out-phase. And we apply many ratios between the normal stress and shear stress. And then we selected few criteria only for documentation, not for decision, only for documentation, which problem become with additive materials with this non-parallelism. This is well known. Findlay is very old. Criterion Cateri Spagnoli is probably from Italy, is also well known. Dangwang is very often used in finite element simulations, it's included in the software. And this is the other criterion from University MDC. Here's a comparison between the calculation and between the experiment. If it's on this line, this is perfect. If it's bottom of this line, this is on the safe side. If it's on this in the top, this is a dangerous side. This is the Findlay criterion, in-phase, out-phase for stainless steel. Here's the relative good correlation. Here's the correlation on the safe side. No correlation, but on the safe side. Here's Carpenter Spagnoli, in-phase, relative good correlation for this same steel, but it's not applicable, this criterion, for out-phase. Non-proportional, yes, out-phase is non-proportional, it's not applicable. Also, Carpenter Spagnoli is another material, this is this merging steel. In-phase, on the dangerous side, this is not good. It's not applicable for non-proportional loading. Then Dangwang, this is this finite element method. Included criterion for the merging steel on the dangerous side. This is a very bad situation. For out-phase for the same steel also on the dangerous side. This is a very, very bad situation. For another steel, this is the stainless, relative good correlation, in-phase, out-phase on the safe side. MDC, this is our criterion for merging steel. Relatively good in-phase, also relatively good in the out-phase. And for this stainless steel, also good correlation in-phase, relatively on the safe side, no correlation, but on the safe side with out-phase, that non-proportional load. And now we're discussing why is this problem with applying these approaches, this criterion. Findlay criterion, also characterized Spagnoli, also Dangwang, considered as a one of parameters the ratio between the conventional, particularly between normal stress and shear stress. Also here is visible, here is visible, also here is visible. And there is a problem for the materials which have no parallel curve in normal stress and shear stress, because here is the fixed constant ratio. If this ratio changes during the lifetime, is the problem, and correlation can't be good. In this, our criterion is a different approach. Here's the mentioned only this slope of this curve, not fatigue limit, slope of this curve, and this slope we come to the better correlation with this logical if this parallelism is not present. We try to also create a simulation about this defect, this dangerous defect with this very sharp notch in the pure tangent, and we rotate by this orientation, but this orientation of this sharp notch. And we try, yes, and we obtain results from the stress distribution. It's very interesting in this table. Which effect is had this rotation, this position of this defect in the loading process, in the pure tension. This is the angle, and this is the stresses. We investigate shear stresses because it's well known in fatigue that shear stress is the most responsible value for the propagation of fatigue greater than the other. And this change is not important that these numbers only for comparison. That the difference between the highest and lowest shear stresses due to the change of orientation is more than 2 times. This is explanation of anisotropy, orientation of this sharp defect to the loading, to the shear stresses, and also is this result as a is documented as a reason of decreasing of fatigue properties in additive manufacturing, because these are additional stresses in the microstructures. It's possible to say also as a residual stresses. It's possible to say from one position of thinking. Then I try to conclude because time is very low, and this theme is very large. That specific of additive manufacturing materials for cyclic strength, for fatigue properties, anisotropy of mechanical properties are a function of the building of building process orientation, then internal defects, condition of outer layer. This is the biling and defects, and then parallelism or non-parallelism of cyclic SN curve in normal and shear stresses. This is this new specifics, new in comparison in conventional material. That multi-axial fatigue of additive materials is sensitive to the orientation of state of defect. It was documented by this simulation. That criteria containing the conventional fatigue limits, and this ratio when it's fixed is not appropriate, because when this parallelism is not present, can't be correlated good. And what is the very important for the future? The higher degree of standardization of additive manufacturing is very needed, required, because if you buy the same chemical material, the material with two same chemical composition from 2 different producers is not clear, not sure, if you obtain the same properties. Thank you so much for your attention.